Now with this idea, we can go ahead and we can apply Schrodinger wave equation to simple harmonic oscillators. Okay. So there are two ways of doing this. One is called ladder operator way and another is called power series method. The simpler one is the ladder operator method, but the beautiful and the most general application is the power series method. So we will talk about both these methods, ladder operator also and power series method also for the simple harmonic oscillators. Okay. If you write the Schrodinger wave equation for the simple harmonic oscillator, then it is the Hamiltonian will be the same Hamiltonian minus h cross s square divided by 2m d square by dx square, and since it is also a one dimensional problem, so only d square by dx square, no y and z term. Okay. And then the potential energy is m omega square x square divided by 2. This is the Hamiltonian which we will be using for applying Schrodinger wave equation to simple harmonic oscillator. Okay. If we can rearrange this Hamiltonian, if here you have a m term and if you put m here also, then it will be 2m on both sides. So make it m square and write an m here, and then it will be 1 over 2m will be common term, and then we will have minus h cross square d square by dx square plus m square omega square x square. Okay. Now if you remember the term which is used for the Px Hamiltonian, Px operator is minus I h cross d dx. Okay. So what will be Px square? Px square will be minus and minus plus and again I square. Okay. So it will be plus h cross square d square by dx square. Okay. Sorry. It will be minus minus plus and then square minus, it will be minus. It will be minus. Okay. So this is your Px square, and if you compare this with this one, it is Px square, and then m square omega square x square. The moment you have this kind of things, that you have an operator which has this term Px square plus m omega x square, we write x square plus y square, then we can factorize this. Okay. And we can factorize this very easily as x plus iy and x minus iy. If you multiply, you get x square plus y square. So that's what we did in the introducing you the complex number. So if you factorize this, you can factorize this into two parts. One is minus ip plus m omega x and ip minus m omega x. Okay. It should be plus. Plus. Okay. So if you because minus sign already I have given here, so it will be plus. Okay. Now in the next step, we say that each of these, one this one and another this one, can be treated as an operator, and we say we give this a symbol of a plus and a minus to them. The first one is a plus and second one is a minus. You look at this, it's the same term which I have used here. It's the same term which I have used here. Okay. The only thing is that 1 over under root 2 h cross m omega is an additional term, and this term is added so that the results which we obtain looks nicer. We are not the first one to do it, many people have done it, and we get from this one that if you use this term, which is a constant term, 2 h cross m omega, then we can get the nicer results. Okay. So we use this a plus and a minus as 1 over under root 2 h cross m omega is the common term in both a plus and a minus, and we say these are the two operators, a plus and a minus operator. If you use this, then what you can write? You write A, if I write A minus A plus and you start calculating A minus and A plus, what do you get? You get IP plus M omega x and then minus IP, and this, if you multiply with this one, under root will go, and then comes the operator algebra, because the P which you have used is a momentum operator, X which you have used is a position operator. Okay. So these are the operators where if you multiply X with P and if you multiply P with X, they will give you different results. They may give you different results. Also, if you have operator A and operator B, and if you operate in the reverse fashion, B to A, they may be equal, they may not be equal. Okay. But in case of number algebra, it is not so. If you multiply 3 and 4 and 4 and 3, you always get the same results. So sequence of operation or reversal of a number does not change the result, but sequence of operation changes the result in case of operator algebra. So this you will always have to keep it in mind. So if you multiply this IP with this minus IP, what do you get? IA square will be minus and minus will be plus, so Px square. Then you multiply IP with M omega x and you get Im omega Px. See, first P, then X, I have written Px. Okay. Then you multiply M omega x and minus IP, so it will be minus I omega x, first X, then P, so I have written XP. Okay. So this you will have to always remember that the sequence should not change, because it is an operator algebra and it is not number algebra. Okay. Then if you multiply this with this one, you get M square M omega square X square. Now what you can do, I omega is common, so bring I omega outside, and then you have Px minus Xp, and Px minus Xp is the commutator of Px. This is the commutator of Px, and this commutator we have already derived earlier, the relationship for Xp, and Px will be minus IH cross. So if you put minus IH cross here in this term minus IH cross, then what you get is H cross M omega. Okay, and M square omega square will remain there. Okay, I is already there, you have minus I from here, so minus will be there, and I square will become again minus, so it will be plus term H cross M omega. Okay, if you rearrange this, then you get 1 by 2 H cross M omega Px square plus M square omega square X square plus H cross M omega divided by 2 H cross M omega. Okay, we have split the equation into two parts. We have split this equation into two parts. Okay, one with this one, and another first we will combine these two, and the second will be this one, and you get this one. Okay, so it becomes A minus A plus 1 over H cross omega, and operator. This is a Hamiltonian. There is nothing but Hamiltonian. Okay, and you have 1 by 2 comes from here. This and this will go, and 1 by 2 will be there. So what is Hamiltonian? Hamiltonian you get as Hamiltonian is H cross omega A minus A plus minus half. Okay, if you reverse it, and similarly you can get another Hamiltonian with A plus A minus. We have determined now A minus A plus. So if you go for A plus A minus, since it is now, again I said you it is an operator algebra, so the results will be different, and you will get a Hamiltonian like this also. Okay, so what we, and if you do some homework, you should try to do this, and you should try to do this also, that if you calculate the commutator for A minus A plus, it is equal to 1. So now in terms of ladder operator A plus and A minus, we have got the Hamiltonian operator and we have got the commutator for A minus A plus also. Using these ladder operator A plus and A minus, we will be able to find out the energy values, energy eigenvalues, and the eigenfunctions also. Okay. In the next module, we will be talking about these. Okay. Thank you. So, in the last module, I talked about this slide. I talked about that we can convert your Hamiltonian. We have converted Hamiltonian in terms of ladder operators, and these ladder operators A plus and A minus are actually 1 over root under 2 h cross m omega minus I p plus m omega x, and A minus is 1 over root under 2 h cross m omega I p plus m omega x. We have talked about that we can get these values, this value and this value, by factorization of the simple Hamiltonian, which we have already done. If you look at this was the Hamiltonian. This was the Hamiltonian originally. Okay. So, from this Hamiltonian, we talked about these relationships. Okay. Now, if you have this ladder operator, then in terms of ladder operator, we converted the Hamiltonian into these two forms, and both these forms are equally applicable, equally valid. One uses the use of which one is to you will have to use depends upon which of these Hamiltonian will make your calculations more easier. So, that will come with the practice, you will get it to know. Okay. So, this we did it earlier, and now we are trying to we will be using these relationships in order to get the energy eigenvalues. So, what we do that we use A plus psi as a function. Instead of psi, now we are using A plus psi as a function, and we will apply Hamiltonian to this function A plus psi. So, what you should get? H psi is equal to E psi, and this is a function, A plus psi is a function. So, you get the energy eigenvalues. Okay. And if you use this Hamiltonian in terms of ladder operator, the ladder operator, in terms of ladder operator, Hamiltonian is h cross omega, and within bracket A plus A minus plus 1 by 2, and then your function is A plus psi is equal to E psi, simple application. Okay. Now, what you can do is, you can bring this A plus inside, but you will have to keep it on the right side only, 1 by 2 A plus and then A plus. This A plus you cannot bring it here, you cannot bring it this side. This A plus which is on the right side will be here, Okay. So, this we can do, and then you can take this A plus outside the bracket also. Okay. So, this A plus if you take outside, then you have h cross omega A. Since you have A plus on this side, you can bring it here. In this term you also you have A plus, so you can bring it outside, and so you bring this A plus outside, and now you have A h cross omega A plus A minus plus half psi h cross omega A plus. Okay. It should have been A minus A plus. Okay. It should have been A minus, because this comes outside, this should have been A minus, this will be A plus. Okay. So, what is A minus A plus? If you remember, the commutator we have already determined, A minus A plus, commutator is A minus A plus minus A plus A minus is equal to 1. This we have done, and if you use this relationship, then your A minus A plus becomes 1 plus A plus A minus. Okay. So, this A minus A plus we will be replaced, and now you can write 1 plus A minus plus half is equal to psi. Okay. And h cross omega psi is already there. Okay. Now, what you do? A plus is outside, h cross omega A plus A minus plus half plus 1 into psi. Okay. So, this you get. Now we divide this into two parts. We divide this equation into two parts. So, we can write this safely as A plus h cross omega A plus A minus plus half psi and h cross omega A plus psi. Remember, A plus psi is your function. Okay. So, this again is nothing but a Hamiltonian. This is your Hamiltonian. So, you can write A plus H Hamiltonian into psi H cross omega A plus psi, and then you rearrange this. H cross H psi is equal to E psi. So, H psi is equal to E psi we have written, and plus H cross omega A plus psi, and then you can write that if this becomes A plus psi, if you take common, then what do you get? E plus H cross omega. Okay. So, you get E plus H cross omega A plus psi is actually equal to H cross omega, this is Hamiltonian applied to A plus psi. So, you get A plus psi here also and A plus psi here also. This was your function. So, this is an eigenvalue equation, and when you apply your Hamiltonian in terms of ladder operator on function A plus psi, the energy which you get is E plus H cross omega. And if you remember, we talked about that quantum mechanical harmonic oscillators have equispaced energy levels, and the energy difference between these levels is equal to H cross omega. So, the next higher energy levels you get E is equal to E plus H cross omega. Okay. So, what did we get? The feature is that A plus psi is an eigenfunction of Hamiltonian with an eigenvalue of E plus H cross omega. E plus H cross omega is the vibration energy of next vibrational state, because the vibrational states are equispaced and the energy gap is H cross omega. Similarly, if you do this with A minus psi as a function, then you should get E minus H cross omega. So, you will get one step lower energy. So, using A plus psi gives you one step higher in energy, and using A minus psi as a function gives you one step lower energy, and that is stepwise. You can go from 1 to second, second to third, third to fourth, or from first to second, second to third, third to fourth, and so on. Okay. So, you can come down also, you can go up also. That is why it is called ladder operator. Okay. Therefore, A plus and A minus are called ladder operator, because using A plus and using A minus, one can rise the energy levels and one can come down to the energy levels also. But in every case, you will do it one step each time. You cannot, you will not jump. You will go from first to second, second to third, third to fourth. If you are using A plus, if you are using A minus, then fourth to third, third to second, second to 1, and 1 to 0. This way you can go up and down. That is why they are ladder operator. With A plus you are going up, so it is called raising operator, and with A minus you are going down, so it is called lowering operator. Energy increases if you use A plus, raising operator. Energy decreases if you use A minus, lowering operator. Okay. So, these ladder operators are used when one of the energy level is known. You can use ladder operators and climb the stairs up, or you can climb it down also using A plus and A minus. Okay. So, if you know one of the energy levels, you can calculate others. If you know one wave functions, you can calculate others. So, the utility of ladder operator is, the beauty of ladder operator is that only one wave function should be known to you, rest you can calculate using the ladder operator. Okay, each at one time. So, the ladder operator makes the treatment of simple harmonic oscillator very easy. Okay. Now, if you suppose the wave function for the lowest energy state is psi 0, okay, and if you try to apply on this wave function a minus operator, then any energy state, any quantum state below psi 0 is not possible. You cannot have an energy level less than V is equal to 0. Okay, you cannot have a V value cannot be -1, -2, -3. Okay. So, the lowest energy state if has wave function psi 0, and then if you apply A minus to this wave function, that has to be 0, because no energy level can exist below psi 0. No quantum state can exist below psi 0. So, if you operate with a ladder operator A minus on psi 0, the value of this must be 0, okay, because anything below psi 0 should not exist, okay. So what we say is that if this is your operator 1 by 2 h cross m omega ip plus m omega x psi 0 is equal to 0. This is your A minus. This A minus operator operating on psi 0 must be equal to 0, okay. And what will happen if you do this, then IP is equal to what? This is a linear momentum operator. So h cross d dx m omega x psi 0 is equal to 0, okay. And the linear momentum operator I have written h cross by I d dx or minus I h cross divided by d dx, both written, okay. So if you use this operator, you get this equation, and so we can write h cross d psi naught divided by x m omega x psi 0, okay, this we can write. And for this equation to be valid, either of this term is 0, either this is 0, constant is 0, 2h cross m omega which you have used everywhere, or this term is 0. Naturally, we will take, in order to get the meaningful results, we take this as equal to 0. So what happens? This, it means h cross d psi naught divided by dx is equal to minus m omega x psi 0, okay. This we can write, and if we can write this one, then we can write psi 0 x dx, okay, a simple rearrangement, d psi 0 divided by psi 0 and then psi 0 x dx. Now we can integrate this equation, and if you integrate it, what you get? This is the integral, and if we integrate without limit, then what do you get? H cross ln psi 0 minus m omega x square divided by 2 plus a constant, okay. If we suppose that h cross ln a as a constant, then we can write the above equation as ln psi 0 a divided by minus m omega x square divided by 2h cross, okay. Or we can write psi 0 is equal to a exponential minus m omega x square divided by 2h cross, okay. So this is the wave function for the lowest energy level we have found, but the wave function is there. This a constant we do not know, so treat it as a normalization constant, so that the normalization condition you apply and find the value of a, okay, which we did earlier also. We found the Schrodinger wave function for simple particle in a one dimensional box, and then we normalized it, same way we did for others also, okay. So we have found the wave function psi 0, and now treat a as the normalization constant, so that you can write this relationship psi 0 square dx is equal to 1, and this will be equal to the a square integral from minus infinity to plus infinity exponential minus m omega x square divided by h cross dx is equal to 1. It is very easy, you can see, okay. Now the result of this equation comes from the value of this integral, and the value of this integral you can find from the standard integral, and a comes out to be m omega divided by pi h cross raised to the power 1 by 4, okay. So if you put this value, the normalized wave function is equal to m omega pi h cross raised to the power 1 by 4 exponential minus m omega x square divided by 2h cross. This if we represent this m omega divided by h cross by a symbol beta, then the easiest way of writing this will be like this one. We will see the value of beta when we will be doing the power series method. So what we did, we tried to apply a minus to psi 0, and I said you that if you apply a minus, means you are using a lowering operator, and lowering operator to which wave function? Psi 0, which is the ground state wave function, and any state below this ground state should not exist, and if it should not exist, then a minus psi naught should be equal to 0. We have started from this point and we got the value of the lowest energy wave function, okay. So what about the eigenvalues using the ladder operator? So after finding the eigenfunction, we will use this Hamiltonian. We have already arrived at this Hamiltonian, and if you use this Hamiltonian and you use the psi 0 wave function, then you get this equation with the Hamiltonian h psi, or you can write this one. Since a minus psi naught is equal to 0, this a minus psi naught is equal to 0, okay. So, what will happen? You will have this part will become 0, a minus psi 0, and so this part will be 0, only this part will be left, and you will have h psi naught is equal to 1 by 2 h cross omega psi 0. So, half h omega h cross omega is the 0 point energy. It is very simple, getting energy eigenvalue. Just write the Hamiltonian in terms of ladder operator and then use the simple logic that a minus when you operate on psi 0, the function should be 0. The value a minus psi naught should give you 0 value, because no quantum state should exist below ground state energy level. So, we have found this one. Can we find the higher levels also? Higher level energy and higher level wave functions also? Yes, we can. Okay. If you use this Hamiltonian on a plus psi, you will get E plus h cross omega a plus psi. This we did earlier also. Okay. So, now we can write E1 is equal to E naught plus h cross omega, or half h cross omega plus h cross omega means h cross omega 1 plus half. Okay. Or similarly, if you use a plus on psi 1, okay, and then you use the a plus psi 1 as the function, a plus psi 1 as the function, then what you get? You should get E1, because psi 1 is here, so E1 is here, and then one step above h cross omega eigenvalue. Okay. Therefore, E2 if you write, then E2 will be E1 plus h cross omega and h cross omega 1 plus half. So, it will be h cross omega into 2 plus 1, 2 into 1 plus half. So, this is also there. So, it will be 2 into 1 plus half. So, this way you can find out the energy for other values, and the general equation which you can write is EV is equal to EV minus 1 plus h cross omega, and means h cross omega is equal to V plus half, where V is equal to 0, 1, 2, 3 is the vibrational quantum number. Okay. So, using ladder operator, we can find out the energy value also, and we can find out the wave function, a normalized wave function for simple harmonic oscillator also. Okay. We can go ahead doing it for the other states also, and since omega is 2 pi nu, so we can write it in the terms of h nu V plus half also, which we talked about, that this we should get. Okay. We can get other operators also, next higher level wave functions also, next higher level energy value we have seen, and next higher level wave functions also one can obtain. If you go for this one, a plus root under 2 h cross omega minus I p, this is your wave function. All these we have already determined. Psi 0 value we have determined in terms of beta, in terms of m omega, and this a plus. Okay. So, with the help of these equations, one can find out the higher level wave functions also. So, in order to do that, what you will do? If you have to find out psi 1, then you will operate, okay, with a wave function a plus psi naught you will use. Okay. And this will give you this psi 1 is equal to a1, and then a plus is 1 over root under 2 h cross m omega minus I p plus m omega x psi 0, and this is going to give you this one. Okay. So, a1 1 over root under 2 h cross m omega, and then you have a minus I p. So, minus I p will minus h cross d dx of which psi 0, and psi 0 you have this one m omega. So, psi 0 value, this is psi 0, nothing but psi 0, okay, and then omega x again multiplied by psi 0. Okay. So, if you do the differential and then do the calculations, what do you get? d dx of exponential minus, you have to find out this differential in the next step, and these terms are as such, no changes. So if you differentiate, what do you get is this one, m omega 2x divided by 2h cross, 2 and 2 will go, and you will see that after differentiation this remains as such, there is no change, this is psi naught, this is psi naught, okay, this does not changes, and then you have m omega 2x divided by 2h cross, all this, then what you get? You get x I have kept here, and rest of the thing we have brought here, and then you can write m omega and x you can multiply here. So you have x here also, you have x here also, this term you have here also, this term you have here also, you have m omega pi h cross 1 by 4, and you have m omega pi h cross 1 by 4. So this term, this term and this term is also equal. Okay. So what do you get? Two such terms, so multiplied by 2, and then you have m omega is equal to this one. Okay. So this you get easily because both the terms are similar. So I have put 2 here, and then you can get this one. Now you use normalization using a standard integral gives a1 is equal to 1. If you use normalization using a standard integral, what you found, a1 is equal to 1, and if you use this a1 is equal to 1, then what do you get is psi 1 is equal to root under 2 m omega h cross m omega pi h cross 1 over 4 pi 1 over 4 into exponential this one, okay, x exponential minus m omega square x square. And if you use again m omega divided by h cross as beta, then you get psi 1 is equal to beta divided by pi raised to the power 1 by 4, and then you have root under 2 m omega divided by h cross. So m omega is beta, so it's 2 beta, okay, into x, so root 2 beta into x exponential minus beta x square, and this we can rearrange. Next higher level wave function is found here. Okay. So next higher level energy we have found, next higher level wave function we have found the ground state wave function also, we have found the psi 1 also, so psi 0 and psi 1 we found, and then I said you that we can find out psi E0 also, E1 also, and EV also. So all higher level energy, all higher level wave functions can be obtained using the ladder operator for simple, and this is the treatment of using ladder operator for simple quantum mechanical simple harmonic oscillations. Okay. So this is a very simple, easiest way of doing simple harmonic oscillator. When we go for power series method, it is a little more difficult, involves more mathematics, polynomials also, and if you are able to do it, if you many of you are from chemistry background, you may not have done much of mathematics. So if you have not done, I have done every step for you, so that you should not feel any problem. And even if there is a problem, we will go for a live session, and you can keep yourself ready for the asking those questions. But be sure of it that whenever you do quantum mechanical, whenever you go through these modules, you must have your pen and paper copy ready, and you should do it on your own. You should not just watch the video and you will not get much of it. If you just keep on watching the video and if you want to learn actually quantum mechanics, then you must have your pen and paper ready, and you should do all these calculations which I have shown in the slides on your own. And further you should do some of the calculations which I have not shown also. I said you a minus a plus commutator is equal to 1. So try to find it out whether it is 1 or not. Okay. So I have derived one of the Hamiltonian equation using a minus a plus. The other one I did not derive. I said similarly. So do the other one also. Do it yourself. Then only you will get the confidence of doing calculations in quantum mechanics, and you will be able better placed to do the assignments which I will be giving for you for these modules. So in the next class I will talk about power series method for Schrodinger equations of simple harmonic oscillator. Thank you.